Remember what I said from the first class? It's to watch the videos and read is not enough. To copy and paste codes is not enough. You have to practice and practice. You have to type them out. You have to look for different ways to do the same thing. The way I'm going to do something is different from the way someone else is going to do it. It's different, though I might get the same results. There are different ways to do the same thing in R, and that's the beauty of R. It's very flexible. But the same way you've done your code today is not the same way you're going to do it next 2 years. All right. Now, the objective of today's class today will be studying linear regression, simple and multiple linear regression, and we'll be learning about the basics. Next week, we'll dive deeper into regression. All right, so objectives at the end of this class, you should be able to test the assumption of simple regression, carry out simple regression analysis, test the model fit for simple regression analysis, create publication-ready graphs, test the assumptions for multiple regression. So we're just going to do the same thing for multiple regression. So that would make us understand more and at least maybe gone through the same concepts 2 times. So the first time would be for simple linear regression, and the second time would be for multiple linear regression. We are testing the same assumptions, and we are, of course, for the analysis, we have a little bit different things for both cases. Now, the content in broad, we have simple linear regression, multiple linear regression, and checking model fit and assumptions. Data we'll be using, we have the HAT data for simple linear regression, and the income. Okay, the income data is for the simple linear regression, and the HAT data is for the multiple linear regression. All right. So without wasting time, we'll talk about linear regression. Most of us may not be new to these concepts, but only with SPSS and Starter, for those who are in Starter class, and several other softwares. Now, linear regression is a regression model that uses a straight line to describe the relationship between variables. It finds the line of best fit through your data by searching for the value of the regression coefficients that minimizes the total error of the model. Now, we've done in the visualization classes we've done in the part A and part B, we did something similar. We passed the linear fits, the line through the scatter plots. All right, so today we'll be looking at the calculations behind that line. There are 2 main types of linear regression. You have simple linear regression. It uses only one independent variable, and of course, one dependent variable. While multiple linear regression also uses 2 or more independent variables. So once this will be variables. So once you have independent variables more than one, you are performing a multiple linear regression. The independent variables are also called the predictor variable, and there are several names that they are called in different fields. But the general umbrella name, you have the independent variables and dependent variables. So the independent variables are the predictor, while the dependent variable is the exposed variable. That's the predicted variable, the variables we are trying to predict. All right. For the simple linear regression, it uses only one dependent variable. Now, the income data has 2 variables. Income, it ranges from $15 to $75. In thousands, that's $15,000 to $75,000. And the happiness scale. So the income data has 2 variables, income and happiness. Now, for a simple linear regression, the model we are trying to fit is this simple model where the y is the response variable. Like I said, it has several names, so I might be using these names interchangeably. Response variable is the predicted or the dependent variable, while the x is the predictor or independent variable, is happiness. Okay. A and B are constants called coefficients. All right, so this is the coefficient of the model, or the intercepts. If you're familiar with the straight line equation, while this is coefficient for the independent variable. All right. Okay, so just a quick one. I think I might have put this upside down. But when we get to R, we'll confirm that. All right. Now for regression, we have 4 major assumptions, and they are the independence of observations as autocorrelation. We'll see how these are carried out one after the other. Now, because for simple linear regression, because there's only one independent variable, we might not need to check for autocorrelation. Autocorrelation has to do with to check if the 2 independent variables are correlated, if they are related, if they are dependent on each other. Okay. Now, if of course we do that by using the correlation analysis, and if the correlation value is strong, then we say that they are not independent, and we might have to drop one. We might have to drop one of such variables, depending on how many variables we have that are strongly correlated. All right. Also the assumption of normality, we've done this extensively in like 2 classes ago. How to check using the graphical method and the formal method. Then the linearity as well. This has also been done. We'll see all of that. But I'm just going to explain this in my own words. Then when we get to R, we're going to test them out. So the linearity is basically check using scatter plots and see if the dots in the scatter plot tends towards a straight line. Does it do the dots, do they look like a straight line, or they are scattered everywhere? And sometimes we put the add the regression line as well. Then for the homoscedasticity, this means that the prediction error doesn't change significantly over the range of predictors of the model. We can test this assumption later after fitting the linear model. All right, so basically for this, what we are checking is when the model has been fitted, then we check, it's usually checked after fitting the model. When the model has been fitted, we check if the errors per observation, if their distance to the regression line is not too varying, then we say this assumption has been passed. All right. Okay. The simple linear regression in R. So basically, those are the 4 for both simple and multiple linear regression. Linear regression. So for simple linear regression in R, basically we'll be using the LM function. LM function does the linear model for us, and it comes with base function in R. It's not as a result of that package. Always examine your data, that's the summary data. Then after testing for some assumptions, run the analysis. Then after, okay, so running the analysis is this is like the free to it. LM, I'm sorry. Okay, so LM, that's the function for linear model. And then the dependent variable usually comes first, followed by this sign. The sign is called, let me maximize this. The sign is called tilde. It will be in different places in different systems. Thank God you don't have to type it. You can just copy and paste for now. All right, so the tilde sign, then followed by the independent variable, then you specify the data. So now this is the framework for simple linear regression. And of course, there are some other things that can be arguments that can be passed into it, but this is the general framework. Now, this has been assigned into objects.lm. It's usually good to make your object as descriptive as possible. Don't just give it a name and give it chair or give it table. No, let it represent something. So we know this object.lm means the linear model that is talking about objects, if that is what it is about. Now, to see the results of the linear model, we run summary and the model. Since the model has been saved into this object, so once we run summary, it brings out the detailed outputs. Then another thing we can do with simple regression is to do predictions, it's simple or multiple, or any of the linear models. So for predictions, we use predicts objects.lm. That's the model we have in objects.lm, and then we pass the new data. So this new data can be tricky. Here I have made like 2 or 3 examples in this class. I mean, for this class rather. So it should be a little bit easier after the class. All right. Okay. So for it not to be too vague, let's go into R and try out all the things I've said so far on the assumptions of simple linear regression, carrying out simple linear regression, making predictions using simple linear regression, and then creating a chart, a representative chart, publication ready chart, that's what it's called, using simple linear regression. All right. So the normal routine that we do when we're about to start any project is to create a working directory. And like we said, a working directory is simply a folder anywhere in your PC. Well, it's advisable you put all your R work somewhere. Anytime you just want to save it, know where your working directory is. All right. So for me, my working directory is on my desktop, and it's called PiLAF_R. So if your working directory is different, all you need to do is go to that working directory and double click the address bar, double click the address and copy this put it, then come to your R and put it inside this code. Of course, when you put it inside there, you may have to change the slash from backward slash to forward slash. All right. So once you've done that, you can run and changes my working directory into the PiLAF.r, underscore R. Now we'll be using these three libraries. The tidyverse. Remember, in the last class I took, I said tidyverse contains some data wrangling and ggplots as well. So you might see someone else's work and they're using ggplots, and they're also uploading deep layer, that's dplyr library or package. They are all in here. So I'm going to run all of them together. Then the new one is the ggpop-r. If you don't have ggpop-r, you can install it. You already know how to install now. An easy way of installing is to click on packages here in the files section where we have files, plots, packages, help. You can easily do install. Then type the ggpop-r in. Okay. Yeah, so just type, you can type it there. All right. So I'm going to load this now. My libraries are still running. Okay, so so in case you don't have the ggpop-r or broom, yeah, to might be new. You can just type in here broom and space ggpop-r. ggpop-r, just like the name ggplots, is also an extension of ggplots. So it means ggpublication r. You can use them to create different. In fact, it has a lot of use if you are writing papers and you are publishing different journals. That some of the themes that comes with ggpop-r has already made themes that passes some journal specification. So you can just pass them into it, and then you have your plots. All right. So if you run this, it's going to install Broom and ggpop-r for you. I'm going to cancel it because I have it already. So once you've done that, you can load the libraries. Already, since you are online and you open this, R is going to ask you that there are some packages, these sheets, these script works with that you do not have, and it's going to ask for permission to load them. So by now, you should already have loaded them in your R. All right, so we are bringing in the data again. I mean, the income data. Now, because the income.data is on my working directory, so I don't need to put any file paths, all those long codes to bring in the data. I can just read .csv and the name of my data, income.data.csv. So I have it here. If you click this part, you have the data. So we have X as serial number, then income. Remember income in thousands and happiness, the happiness scale. Yeah. All right. Okay. Now let's look at the summary. The PowerPoint says it's a good practice to always check the summary of your data. It gives you, it tells you a lot about your data. All right. So we have for X, like I said, serial number. So minimum is 1, maximum 498. So that means we have 498 observations. And for income, the minimum income is 1.5, while maximum income is around 7.5 as well. Remember, it's in thousands. And then for the happiness scale, minimum is 0.2, maximum is 6.8. Of course, I've scaled the first quarter, medium, main, and third quarter. And all see them there. Okay. Now, I'm going to bring in the other data that we'll be using for multiple linear regression, and that's the heart data. So to view the heart data as well, you can click the data here, then or the alternative is to type this code here, capital letter V and small letter IEW, view heart data. All right. Emphasis on the capital letter V because it can be frustrating when you're typing V and you're not be getting the results. All right. So for the heart data, we have biking, smoking, and heart disease. We want to check, is there a linear relationship between biking and heart disease, smoking and heart disease as well? For the income data, our interest to check if there is any linear relationship between income and happiness. Income and happiness. The more people, does happiness increase the more people earn, or maybe income is not a predictor of happiness. All right, so we are going to see this in a moment. So simple regression assumption. Remember that simple regression, like we've said just now, has one dependent variable, one independent variable. The independent variable is predicting the dependent variable, is acting on the dependent variable. All right. So for the first assumption, that's independence of observations, also known as autocorrelation, since there are, for the simple linear regression, there's just one independent variable. That's for the income data, which is income. The income is independent according to what we are doing. Of course, there are some things that can cause, that can be as a result of income, maybe age, maybe years of experience, maybe educational level, but that's not what we are concerned about here. So what we are concerned about is, the question is income linearly related with happiness? All right. So what I concern is income predicting happiness. Income is the independent variable, while happiness is the dependent variable. All right. So let me go back to the R scripts. So because we have just one independent variable, we can't check we can't check correlation with something that is not there. So there's nothing to check the correlation with. So we'll skip this for now. When we get to multiple linear regression, we'll check that assumption. All right. Then for normality, normality test, normality assumption, if we try histogram, okay, histogram for income, what's our dependent variable? The dependent variable is happiness. Let me try histogram for happiness. All right. Okay, we have this. Now, this is not a perfect, it's not a perfect bell curve, but it is not too far from being a bell curve. So for the purpose of this, we are going to be using it. Although the Shapiro-Wilk test tells us that, okay, I'm still doing this for income, I should do it for happiness. Oh, okay, sorry, I didn't spell it well. So I don't like spelling anyway. Like, I don't like typing when I'm using a better way of doing it is when you use the accessor and you press tab, it brings the variables. Instead of having typographical error, you can always do that. Right. So like I said, it's not a perfect bell curve, but looking at it, it's still something we can do with. It still looks like one anyway. As a matter of fact, when I was preparing this, I thought this was a bell curve, so it still looks like one. So just get to do that. Then for the linearity, now for this linearity assumption, it is close to performing a linear model as well. So here we are putting happiness as a dependent variable, while income is an independent variable. Remember the tilde sign, and data equals income. The only difference is that instead of having ln as the function here, we are having plots. We are plotting it. We're not looking at the estimates. So now, looking at the outputs here, the lines are like, it's a big straight line. It's like the pattern after along a line. So we can say that the variables are linear and they pass the assumption of linearity. All right. Then for the homoscedasticity, that is homogeneity of variance, which I explained earlier. Like I said, we'll be testing that after fitting the model. All right. So to fit the linear model, we'll be calling maybe the objects. Like I said, the object should be, you should give the object, just for your own sake, not for R. Give the object something as descriptive as possible. So this is income happiness. That's income predicting happiness in linear model. The name can be done for some people, and you can also use, okay, just anything is fine. But for me, I like it to be as descriptive as possible. All right, so the LM command, which stands for linear model. Now, happiness on the left-hand side, the dependent variable always comes first, then the independent variable. Now, from which data are we using these variables? As the income data. If we run this, the model has been fitted, but there's no outputs. That's because we have not called the object that we assigned the model into. So now the function summary and the model brings out the output of the model. All right. So this is a detailed output. We have the formula coming up again. Then for the residuals, we have the minimum to the maximum. Now the coefficients is where we are going to. Remember, it is simple linear regression, and we have one independent variable. Now, the dependent variable is not going to show here because it is what is being acted on. We are reporting it. We are reporting these numbers with respect to the dependent variable. So we can say that income has 71%. I mean, 71% effect on happiness. All right. So we can say that, and we can also say that 71% of income is related to happiness, like 71% of the time. So for simple linear regression, there's really nothing much to check. Another thing we need to check is the p-value. The p-value for the coefficient for income is 0. Like we have 16 zeros before 2 and 0.000 before 2, which is very, very close to 0. So that means this is significant. The linear relationship between income and happiness is significant and it is strong. We have 0.71, which for simple linear regression, this coefficient usually gives us the same thing or almost the same thing with the correlation value. So we can say here that income and happiness are significantly and strongly correlated. They are related linearly. I don't want to use the word correlated, but they are related linearly. All right. So for the general p-value to always have the same thing, because remember we have just one independent variable, so they are not two. So the general p-value will not change. Neither will the adjusted R-square. They are always for simple linear regression. They are always almost the same thing. All right. So for this study or for this experiment, we can say that income is linearly related to level of happiness or to happiness. So the more people earn, the more happy they are. All right. Now we can also the model that we fitted, we can use it to predict as well. Now to do the prediction for simple linear regression, I remember that what we used in fitting the model is a data set. The data set contained income and happiness. So to predict as well, I remember we are using income to predict happiness. So to predict happiness, that is not like if someone is earning a strange number, a strange figure, this person is earning 12,170, and perhaps this number is not in our model. We don't know it before. So now that we fitted the model, we can use this number we can pass this number into the model, and the model is going to give us the expected level of happiness that person should have as a result of this income. All right. So now that's why we are doing data frame. We are making income equals, though it's just one observation, we are still passing it as a data frame because the model takes a data frame. That's data equals income. All right. So I'm going to run this. I'm running this as a data frame. So A is a data frame. You can see it's under data here. So it's a data frame with one observation and one variable. If I click it, you have one observation and one variable. Yeah. All right. So from okay. So to predict what level of happiness this person would have, the person who is earning 12,170. I'm saying 12,000 because we established at the beginning that the income is in $1,000. All right. So we pass this into, we use the function predicts. Then the model that we've created, income.happiness, sorry, control Z. Yeah, income.happiness.ln has the model we established earlier. Then the new data, which is A. We are trying to predict happiness. The data we are passing in should not have the happiness value. So we only have the data available to us is the income. And we want to use the income to know what is not available. That is the happiness level of that person. So if we run this, we have nothing because all of the function predict has been assigned to results. So if we print results, we would see this person is having a very high. Remember, I also said that the happiness scale ranges from 1 to 10, although it is a continuous variable because it has points. I mean, it's in several digits. So, okay, that's like 1, 2, 3, 4, 5, 6, 6 digits, 6 decimal places rather. All right. So it's a continuous variable, but it's ranged from 1 to 10. So this person earning $12,170 we are predicting that this person would have happiness scale happiness level that is very high. That's 8.8, almost 9 level of happiness. All right. So remember, there's one assumption, which is the homoscedasticity. Now we've not checked. Now to check for that, we use the function plot, and we put the data into, the model into plots. So plotting this model will give us, it's going to give us a very, at first you won't see anything, but if you read the output here, you have it return to see next plot. Return means your enter. So if you press enter, you see the residual versus fitted plots. Now for these plots, what we are looking for all the, it's going to give us 4 plots. All the 4 plots, what we are looking at for is this red line and how the data points are distributed around it. When they are distributed evenly around it, then we can say they are the assumptions are passed. So the assumption for homoscedasticity is passed for each one of the 4 points plots. Basically, there are 4 plots saying it's showing the same thing. And we have the QQ plots as well. And we've gone through this before as well. So most of the data points fall around the trend line. So again, the model is fine. And then we have the scale location. And so for all of them, you can see that the red line is around 0. And then the points, the points, the predicted points all fall around the red lines evenly. So we can say that the model is good. It passed the level of, the assumption of homoscedasticity. All right. Now, a better way of plotting this is to use this function, these 3 line functions. The PAR the function creates a framework where we plot data. We will plot our graphs. The framework can be different formats. I know we didn't talk about it during the visualization class, but Prof has used it once, and I just feel I should stress it. This 2 by 2 here means that we have 2 rows and 2 columns. Remember, I said it's going to give 4. It's going to give 4 plots. So it's going to arrange those plots into each column of the framework. All right. So let me just run it and you see what I'm talking about. So the 4 plots are going to appear here, and then we can see them better. Let me zoom. All right. So for the first one, we have the residual versus fitted plots. Like I said, the red lines are important. They have to be around 0, and then the lines should be evenly below and above the red line. Then for the QQ plot as well, it is the diagonal, the line of diagonal. If the dots are around the lines, majority of the dots are around the line, then we say this assumption is passed. All right, same thing for the 2 other plots as well. All right, now, okay, then I have the plot interpretation here, which we can read up for the first plot, residual versus fitted, the normal QQ plots, then the 3rd one and the 4th one. But I'm not going to do that now. If you have time, I'll come back to read it. So something we can read up. Now, to visualize the results with the graph, I want to finish simple linear regression, then we'll take questions before we go into multiple linear regression. Now we've done the model, we've seen the outputs. Now, so just go further for presentation's sake and being more explanatory in our analysis. All right, so for simple linear regression, to visualize the results, we have GG plots, income data, then the X is income and Y is happiness. All right, then geom points, very straightforward. It's going to plot the scatter plots. Here we'll have a scatter plot that is just a normal scatter plot. Then we can pass this is normal scatter plot. That the same thing we plotted for that assumption of linearity. So this time around, we want to pass the trend line into it. And doing that, we're going to add. Remember, we have our ggplots, income.graph. Then, so the income.graph is all here. Sorry, Control Z. Okay. Income.graph is here, then plus geom smooth, this additional function that we are adding. Yeah, geom smooth, method equals lm, and color equals black. So this is going to add the regression line into the scatter plots. So add the regression line into the scatter plots, and you see how well the line fits into the scatter plots. Okay, a moment. Okay. Yes, you come up now. All right. So we have the regression line in the scatter plots. You now want to go a little bit further by adding the equation into the regression line. There are two ways of adding the equation. You can add it automatically, or you can add it by using it as label. Since we know the model already, so we know the output of the model, we can add it as label. But the function start reg line equation would help us to do it automatically. Now, this label.x3 and label.y7 is only telling it the position to put the regression equation on the graph. It's saying that where x is equal to 3, so 3 should be, this is 2 and 3, 3 should be in between 2 and 4 rather. Then when label y is 7, so it's going to put the equation like this stuff from around here. Let's plot this and see. Then run the income.graph. Okay. Again, we have to wait just a little for this. All right, so you can see this is between 2 and 4, 3. The coordinates of 3 and 7 is where it has put the regression equation, because the simple linear regression. So the intercept is 0.2, and the coefficient for income is 0.71. So what does this mean? It means that for every unit increase in income, maybe for every $1,000 increase in income, people have additional 0.71. People's happiness increases by 0.71. But every time their income increases by $1,000, then their happiness level increases by 0.71. So that's the model we just fitted using income and happiness. So we've seen that there's a linear, the relationship can be fixed. They are linear. Yeah, the relationship is linear, sorry. And fitting it, we see that for every simple increase, that means every time x increases by 1, happiness, that's the value of y, will increase by 0.71. Because 0.2 is a constant, so it's a constant. It's not going to affect how the result changes. The only variable that is here is the income. So every time income increases or decreases, the same thing happens to y here. It either increases or decreases as well. Now let's create a publication ready graph. We already have this graph inside the income.graph. So all we are doing is just add a theme, black and white. Most papers are printed black and white. Then the labs, the title, the x, the y, and all. So we are going to run this. It's just going to post a black and white thing, and then gives it proper recording and a proper labeling for the axis and the main title. All right. So here we have it, and can be downloaded and added into the study that is being developed. So this is the regression, simple linear regression, income predicting happiness among these roughly 500 people. I think 488 or 489 people. All right. So let's take a pause here and use 4 questions.
Yeah. So I want to ask, with the regression equation, does it mean that if we have a value of for income that is not in the data we used, let's say
in the data,
we can get the corresponding value for the happiness.
Yeah. Okay. So okay. Now this is simple linear regression, and it's very basic, like fundamental predictive analysis. All right. The way it works is, if it starts from having a good model, starts from a very good data collection process. Data collection is good, and all the assumptions are good and all. So what the model does, it models the relationship between the income and the happiness. Now, given that the model and the income and the happiness has already been captured properly and modeled properly, we are assuming that no matter the income level that you bring, even if we don't know the person, we just know this person earns this amount, then if we put it into the model should tell us that the person should have this level of happiness. Now, another thing is, remember that this is simple linear regression. Income alone cannot make people happy. So the person might be, so if it's a real life study or a real life investigation, we might want to check more than income, and that's where multiple linear regression comes in. So probably not only income makes people happy, maybe there's some other things, the part of the world they live, and all of that. A lot of things you have to do extensive studying to get all the variables that can predict income. But we are assuming here that in this analysis we've done, that income alone is able to predict people's happiness. So given if that is true, then you can bring someone's income, then we'll tell you the level of happiness. And of course, we've also seen the level of significance that we are sure that 95% of the time this would work, it will be true, that this model will be true. So there are more sophisticated ways of ensuring that your model is true, like so much more that is beyond this class, more rigorous ways of ensuring that the model is true. But for now, for the scope of this class, it is the answer to your question is yes. You can bring someone's income and put it into this model. But don't forget, this what we are doing is fictitious data. It's not real data. All right. So you can bring someone's income and put it into the model, then to predict for you. All right. So I remember, let me just say a little joke to lighten this. So my brother saw my work and was like, this is, he told me to explain. I explained to you. So we now asked that, can we use to predict sports betting? So I told him, if he can measure the variables very well, then we can do that. But we have to study a lot to know what goes into those things. And I'm sure they also are not, I'm sure they are also not dumb to make it so simple that anybody would get their methods. All right, so that's for simple linear regression. Remember, simple linear regression, one independent variable, one dependent variable. And simple linear regression, they should be scale variables, continuous variables. Though simple linear regression would, sorry, not just simple regression, regression would take both scale and categorical independent variables. But just don't you shouldn't have too much categorical, but it will work. It's like almighty formula of predictive analysis. All right. So multiple linear regression.
Yes, sir. What you're saying now is that if you have a categorical and a continuous, like,
yes. So if our dependent variable is income and gender,
yes,
for example, so we can still run a regression analysis.
So the categorical will be the dependent or the independent?
No. Okay. So if in that case, if the categorical is dependent, that is another analysis entirely, which we will still get to. That's logistic regression. What I'm saying is for independent variables, the independent variables are the ones predicting the dependent variable.
Yes,
so the dependent variable is people's happiness. Now, so we can only predict one thing at a time. So the dependent variable can just be one. So what are the things predicting the happiness? Is it income? So is it income? Is it gender? Is it age? So in that case, we have two continuous variable, income and age, and we have one categorical variable, gender, male or female. I'm sorry.
Right. I understand.
Yeah.
Thank you.
Oh, sorry. All right. Oh, I'm so sorry. Multiple linear regression. So for the assumptions, again, those four assumptions: independence of observation, autocorrelation. Then so for that, use the correlation function. Then the normality, assumption of normality, assumption of linearity, then homoscedasticity assumption. So because I used close to 1 hour to explain simple linear regression, I'm going to assume that multiple linear regression is going to take more than that. So I'm going to try and run through this. So the estimated effect of, so what I want to look at in that data is the estimated effect of biking on heart disease and the estimated effect of smoking on heart disease. Okay. So for the multiple linear regression, not for what I just, for multiple linear regression, the model framework is like this. It can be written anyhow, like there are several forms. So this is just me doing something. So the coefficients again, this time around we have two independent variables. Forget this guy here. This one just means that you can have more than two. You can have 3, 4, 5, 6, 7, 8, and so on. Then the error value for the model. All right. So let me just go through the rest of this, and I know I'm forgetting the PowerPoint. Okay, for the homoscedasticity, it's the same thing as the simple linear regression. Like I said, most important thing is to look for the red lines. Then these are repeated. These are repeated thing. Okay. Then the predicts as well. Then make the graph. Then we have a small assessment here. Yeah. Okay. This is just the class evaluation is a self-practice. Then the assignment will be dropped on the Google page. All right. So let's go to for multiple linear regression. Then we test the assumption. For the first assumption, independence of option. For this one, let me show you the data. The hard data. We have three variables. One, remember the dependent variable can only be one. Okay. So, okay, the dependent variable can only be one, and that in this scenario, we have heart disease as the dependent variable. Then the independent variables here are two. Remember, multiple linear regression. A regression is multiple once the independent variables are more than one. Once they are more than one, it is multiple. Can be 2, 3, 4, and so on. All right. So here we have two continuous variables predicting heart disease, and the continuous variables are biking, smoking, and heart disease. I mean, sorry, biking and while the predicted variable, that's the dependent variable, also a continuous variable. Now, something about this data is that the data is in percentage. So the percentage of people who we have like 500 group. Let me do the summary again. Let me just do the summary here. Summary hearts health hearts.it. Okay, sorry. All right. I don't see the okay 498. All right, that's 498. So it's also a fictitious data. So we are saying among we have 498 groups of people. I'm just trying to explain why this is in percentage, like less than 100. All right, so 30% of group one, they do bike, and 10% of them smoke. 65% bike, 3.2% smoke, and so on. So then the percentage that have heart disease among them are these guys. All right, so we have two dependent variables, one dependent variables. Yeah, continuous variables predicting another continuous variable. Now, to check the first assumption of independence, we are checking if the two predictor variables, those are the independent variables, are they related? So to do that, we use the correlation test. The correlation test, we do that by using the function COR. It's a base function in R. A base function means that it comes with R. You don't need the package to run it. Okay. So if I run this, it's going to give me correlation value. For those who are not used to correlation, correlation is a test of relationship between -1, -1 to +1, and in between we have 0. Of course, before you get to +1 from -1, you have to pass through 0. 0 is the middle, and it means that those two extremes, -1 and positive and +1, are strong correlation, either negative or positive. Negative means as one goes higher, one goes lower at a very high rate. Positive means they flow together at a very high rate. 0 means that it is fast. You can't establish any correlation among them. So as a correlation value tends to 0, either from minus or positive, we say the correlation is weak. Tends to 0, meaning that from 0.5, 0.4, 0.3, 0.2, 0.1, as it tends to 0, as it approaches 0, we say the correlation is weak. As it approaches 1, either plus or -1, we say the correlation is strong. All right, so for this, the correlation is weak because it's close to 0. If you approximate this, it is 0. Yeah, because 0.0, the best approximation we can have is 0.02, which is still close to 0. So the correlation is weak. Quick one, you can ask, what if you want to test for the significance? Call the test. Maybe next week we might do more of this. We have this is going to give us the p-value as well. Where is the p-value? Okay, 0.73. So you can see it is not even significant. So we can see there is a significant correlation among them. So this establishes the fact that they are independent. Smoking and biking are independent. It will not make sense to use dependent variables that look alike to predict something. It's going to like, make the model. The model is not going to be good, and the adjusted R square is going to be high. You have like 0.98 or 0.99 or 1 self. All right. So in a case where you have two correlated values or more, you drop some. There are some other variable selection processes that you use to drop them, which we won't be covering here. All right. So we've established the fact that these correlations these variables are independent. Fine. So let's see the normality heart disease histogram. As long as it looks like a normal curve, it's fine. It doesn't have to be perfectly normal. All right. Then the linearity as well. So the linearity will plot each of the independent variable with the dependent variable. As the heart disease with biking, we try to see the pattern. The pattern of the scatter plots is going to look like a straight line. Yeah, this did. It looks like a straight line. However, you can see that. Okay, yeah. So let's go to the second one as well. I wanted to say something because I know the result already. I want to do something. All right. So for smoking as well, let me zoom in so you can see it well. Smoking as well, it wants to not look like a straight line, but sort of it's still a straight line. The straight line might just have maybe the straight line is fat or it has wide width. Okay, so but it still looks like it follows a straight line, which is fine. Again, the homoscedasticity is going to be after we fit the the multiple linear regression. Remember, I explained that homoscedasticity, it measures the distance of the distance of the errors, yeah, along the distance of the errors, yes, the error intervals along the fitted lines. Okay, so just what I explained with the red lines the other time. When we get there, it will be clearer again. So here we are giving the name heart disease LM. That's linear model predicting heart disease. So anyone who sees this should be able to understand. Again, we are using the LM function, and what is different here is how we have passed this into it. Remember, I said the dependent variable will always come first. So the heart disease is what we are interested in predicting. So we are saying that whenever we know the biking status of a group or a person and the smoking status of a group or a person, we should be able to predict if the level of heart disease such person or such community is going to have. Let me just use community so that I won't model things up. All right. So from where? From heart data. Data equals heart data. Now, you might see how these independent variables were stated here. When we did only simple linear regression, we had one, so there was only for plus. But this time around, there is no for plus to state that we have more than one independent variables. All right. So I'm going to run this now. Control Enter, and like I said, because the model has been assigned to this object, heart disease LN, so we won't see anything. But of course, there's something here that has been added here. But if you run summary heart disease model, so we have the detailed outputs. So this time around, we have two independent variables. One of them is negative, the other one is positive. So like I was going to say there, that time I was going to talk about the biking data. Let me go back a little here. So if you watch the biking data, when we plotted it with heart disease, the lines were like in the negative quadrants, while the line here for the smoking is in the positive quadrant, like positive direction rather. The other one is negative direction. This is positive direction. So saying that linearity or that pattern or direction of linearity already tells me something, that biking is going to be negative. Now, what does that imply? It implies that for an additional person that bikes in that for each group, remember we said this is a group of like 498 people, and from each group we are testing how many the proportion of people who bike, proportion of people who smoke, proportion of people who have heart disease. So we are saying that here, this result is telling us here that for every person, every additional person that bikes, the heart disease of that group reduces, or the heart disease, yeah, of that group reduces by 0.2. For every additional person that bikes, heart disease, people who have heart disease reduces by 0.2. While for smoking, for every additional person that smokes, heart disease increases by 17%. So here, for biking, for every additional person that bikes, heart disease reduces by 20%. That is what the negative sign here is saying. While here, heart disease for smoking, heart disease increases by 17, almost 18%, 17.8%, and they are both significant. All right, they are both significant. And then the adjusted R square here is talking about the model, how good the model is, and the p-value is also yeah, okay, so adjusted R square is telling us about the joint the joint effects of hiking and smoking on heart disease. So smoking has a very, very large effect on heart disease, according to this data. Remember, it's fictitious data, so that I won't be quoted anyway. All right. Okay. So that's for the model. The model has been fitted. Fine. Now for prediction, this is going to be quite different. Earlier I said we're going to see different ways of passing data into this prediction. One would be for simple linear regression. It was much easier because simple linear regression takes only one data point. So although we did data dot frame and we did whatever that income equals something. Now this is another data frame, and we need it uses two arguments because two variables were passed here. So in the prediction function as well, two variables need to be passed. So that's why the data frame is collecting two arguments. Biking equals 20, smoking equals 20 as a vector. So if we run this, we're going to have two variables, because if you remember the first class we had, I said vectors are like columns because they can only take columns variable, it can only take one type of elements, while the other one is, I can't remember now. I just have the memory, whatever. All right, so if you look at this, if you look at the new, let's click this. Okay, so we have two variables and two entries, like one row, one entry each, 20 and 5. So what we are looking for is, what we are saying here is that in a group, maybe we have another group, a fresh group of people, where 20% of them do bike, 5% of them do smoke. So can our model predict the number of people who will have heart disease, who are likely to have heart disease in that group, All right, let's see. So use the fitted model to predict the rating, blah, blah, blah. All right, so to do the predict, remember how we passed the predict in simple linear regression, which was passing two arguments, the linear model, then the new data. The linear model and the new data to predict. So that's giving us 11.87. So approximately we have 11.87% of people in that new group where 20% bike, 5% smoke. 11.87% of people will have heart attack. So this is according to the data we've modeled and we are using to predict. So this time around, we are going to draw the four okay. So for the homoscedasticity assumption, these are the plots again. So this time around, we still have the assumptions are still good, like well met. Okay. So the first one, residual versus fitted, you can see the red line is still around 0. It shouldn't be far from 0 at all. The farther it is from 0, the worse the model is. Then again, the dots plotted around the line should be even. Like, do we have the same like evenly plotted? Do we have, looking at it with your eyes, are they like, we have like the same number? How far are they from red below? How far are they from the red above as well? Therefore, the QQ plots again, as long as majority of the dots are on the red line, then we can say the model is good. And the same thing happens is applicable to all of this. In next class is centered more on the assumptions and the model evaluation for regression. All right, so we'll see more of those in the next class. Now, to visualize the results with a graph for multiple regression, we have okay. So now again, for prediction, we are doing two things here. We are predicting and then visualizing the results more clearly using a graph. Now, we want to create a new data frame with the information needed to plot the model. So this is a multiple linear regression, and we need to plot it in a descriptive way as possible. All right. So we're going to create a new data that has the same information or that has the same characteristics as our main data. So we call it plotting data. And this time around, we're not using data.frame because we want to pass functions into it. Not if we want to use the data.frame, we mostly pass vectors into into data.frame to create the data frame. But this time around, we want to pass functions here so that it can create the data set itself. Now, for those who bike, we have sequence. Sequence starting from the minimum value is the minimum in data biking, the biking data, and the maximum here is the maximum in the biking data. So that means it's going to create then length out 30. This means that it's going to create 30 observations, and it's going to start from minimum. It has the same characteristics as minimum for biking and maximum for biking as well in our normal data. While for smoking, we need a variable. Okay, here we are creating 3 intervals with the mean, the median, and the maximum. All right, you would let me just run this and show you the data so that it will be clearer. Okay. So for the plotting data, we have 2 variables. One is biking, the other is smoking. One is biking and smoking. So if you check the summary of plotting data, okay, let me not do that because of time, because I'll have to go back and check the summary of the normal heart data. So the summary is going to be the same minimum and maximum for biking. For smoking, is going to be the same mean and it's going to be the same minimum, mean. Let me see the arguments we used to create it. Okay, it's going to be the same minimum, mean, and maximum. All right. So the data still has the same characteristics. Now, to predict the value of heart disease based on the linear regression we've done. Now, remember the first type of data we used in predicting was just a single entry. That is one row. This time around, we have multiple rows. We have 90 observations there. Now, we use the same model, heart disease ln, and passing the new data, which is plotting data. Right. Now, before I show you that, let me show you this. Now, the predicts, we are familiar with the predicts now, and we've seen what we've done. We've created 90 more observations that was predicted. Everything that has been predicted were stored in these objects, the predicted.y, inside the plotting data. Now, remember the last time I showed you plotting data, we had 2 variables. Now we'll have another variable called predicted.y in the plotting data. So we have 3 variables now. So what we did was to pass a lot of data into it. Then for each one of them, it gave us corresponding prediction for the percentage of people who would have heart disease, in that group, instead of it's one after the other. So doing that, we have a data set for biking, smoking, and heart disease. So we know that the predicted Y actually stands for heart disease. All right. And now remember that what we are interested in is to plot the model in a way that will be seen. We've seen the model evaluation, we've seen it's okay, but we want to plot it in a way that it will be understood better. Now, round the smoking numbers to 2 decimals. Now, the smoking here, we have it in how many decimals? 2 or 5. Yeah, 5 decimal places. So we want to round them to 2. Why I want to round them to 2 is because of the next step. We want to make it factor, like transform it into factor so that we can divide it. All right. Where was I? Okay, so this is going to round the smoking data into 2. The smoking data under smoking variable into 2. Now, that using the function round, and the argument passed into it is the variable, and digits equals 2. To specify then is that 2 digits should become a 2 digits variable. That's 2 decimal places. So let's see what we have here for smoking. So we have 0.53, 0.53, 0.53. Now we have, remember for smoking, what we passed, how we created this was minimum, mean, and maximum. So the minimum for smoking was around 0.53%. Then maximum was 15.44. Okay, no, 29.95. Mean was 15.44. So by default, this is like a categorical data already. So because they are the same numbers coming over and over again. So you can as well change it into factors. Remember, how to change to factor is to use the function as factor. So we add another variable called smoking, which is a categorical variable now. So as factor, smoking. So if you go back to plotting data, So it replaces what we have there before. I can see factor, column 2 is a factor with 3 levels. That's the label it's brought out. It has 3 levels and is now a factor variable. Right. So now to plot data, we plot the original data. That's the normal heart data. X is biking, heart disease, blah blah blah. Scatter plots as well, just like we have in the linear, single linear regression. Okay, so it was assigned to heart of plot, sorry. So I'm calling heart of plot now, and it's going to show this scatter diagram. Okay. All right, so we have this. Then to add the regression line, to add the regression line, we use the geom.line, and the plotting data would help us add that. Okay, this has been taking some time. Okay, okay, I was wondering. All right, so what we did here was, let me go through this code here. We have the heart.plots, which was our normal plot, the normal plot that we did the scatter plot for. Now remember the new plotting data that we did, that we categorized smoking into three categories. So what this did was now to plot a line chart into the heart plot. That's the heart plot is a normal scatter plot that we did earlier. So now this did a line chart. We added the line chart into the model. Now this line charts, these charts are actually two different things. We have the scatter plot and the line charts, but plotting them together showed where the the smoking levels are. So for those who are under in the minimum classification for smoking, the red, that's around 0.5, they're around here. So this can help us to actually know how it represents the how can I say this? Like for those who are in the minimum value, they are around the minimum lines of, the scatter plots. Let me just say that way. They're around the minimum area of the scatter plots. Then the mean values as well. You can see it in the model. Then the higher values of smoking are as well in the upper parts of the model. Now, to make this a publication ready chart, again, all these things we have here are already saved in heart.plots. All right. So again, putting everything into heart.plots can as well use the heart.plots and use the theme and labs again for the headings and all of that. If we run this, we have a black and white. All okay. My scatter plot is always taking a while, so just hold on. Now, the last thing we want to do is to add the regression equation into the chart. All right. Okay. So to add the regression equation into the chart, like we did the other time when we were plotting for simple linear regression, we used a function, but that function is not going to work for multiple linear regression. There are the other functions, but for multiple linear regression, I just put it manually. And how you can do that is to, like I said, add it as label. Now, this annotates. We could have done it in label here, but this annotates helps to put it inside the chart as well to get the same feel that we had for the simple linear regression. So now annotate geom equals text. then the position where we want it to be, x equals 30 and y equals 1.75. So here you can, this helps you to control where the regression equation is going to be in your graph. So x30 is around here, and 1 point should be around somewhere here. So the equation is going to come around here. We can change it if we don't like what it looks like. Now, of course, we've seen the normal output of the equation. The coefficients, the model constant was 15, and the coefficient for biking was minus 0.2. The coefficient for smoking was 0.18. So if we run this now, then we have the regression equation added to the chart. Okay, on this one. Okay, so here is the zoom version, of course, the bigger part. So the regression equation is here. Of course, you can always bring it to maybe change the x to 10, that should be better, or 5. We change the x value from the position here to 5. X equals 5. And y 1.75. I think 1.75 is just fine. It's going to be at the base. If I run it again, it might take time, but I'm going to run it anyway. Oops, sorry. Something's wrong. Okay. Why that was not going to work is because I highlighted something and ran it. Yeah, I highlighted something and ran it. So it was just going to run those things I highlighted, which were not full, codes. So that's why I was saying it's not going to run. And this is going to change the position. Changing the position of x here is going to change the position of the equation to make it better positioned. All right. So for multiple regression, you don't have to come through all this stress I did trying to classify smoking into three, the minimum, maximum, the minimum, mean, and maximum. Once you have your model and you can plot your residuals. Okay, I'm trying to zoom this. Okay. Now, why this is like this? The first why is 15 plus, like the 15 is up and this is down. Maybe because of the size of my charts area here. You can try it again. Or let me say something, one more thing. Sorry. Okay. Perhaps, but I'm not sure. But if you try it and you are still having the same thing, you can try to make it this way. Let it be on the line. Yeah. So I think this would work now. It won't break the equation. It won't break the equation. So it broke the equation because the quotation marks is going to, it means present it as it is, like as it is in the code. So this should be better now. Just a minute. Okay, it's the same thing. All right. Okay, it's not here next. Just want to be sure of that. All right. Okay. At this point, I think I'm just going to leave it, and maybe it's my plot area. We can try several things to see what could actually be the problem. Here it has truncated the beginning of just truncated it. So I can't be okay. Maybe when I fix this, I'm going to put it on Google Classroom. It's not supposed to be a big deal. It's supposed to work. All right. However, for now, we'll be stopping here for simple regression or simple linear regression using one independent variable and one dependent variable. Then for multiple linear regression using two independent variable. So everything we've done here, whether you're using 2 or 3 or 4 or 5, it applies the same way. Like it follows the same pattern. What I would advise is that all of the R scripts you receive today, you can always reproduce them for as long as you are doing the same analysis. You just change the variable names and it should, if it's run here, all things being equal, it should run while you are reproducing yours as well. You just have to change 1 or 2 things. All right. So I guess I'll stop here today. Next week we do more